Now, let us move on to the history of prestressed concrete. As you all know, first, though concrete, the Roman concrete is in use for more than 2000 years, the modern cement concrete started flourishing after the invention of modern Portland cement manufacturing by Joseph Asphodel in the year 1824, right. Limestone and clay, they were burnt together to produce a substance that is hydraulic in nature. So, that is the invention of modern Portland cement. After that, Joseph Monnier, again he was a florist, he invented the concept of reinforcing the concrete. So, when he was making flower pots, the flower pots were cracking, so he put some steel wires. So, even after cracking, the steel wires were able to take the tension. So, in fact, you can say Joseph Monnier actually was the one who has been documented to have invented the concept of reinforcing the concrete. So, then again in 1886, Jackson in the US, he introduced the concept of tightening steel tie rods of stones. In a way, it is called post tensioning, and also in concrete arches. So, by applying using steel tie rods, then you can pretty much transfer heavy loads. So, he introduced the concept of tightening the steel rods, or in other way pre-stressing, first applications of pre-stressing. Then in the year 1925, Dill, he used high strength unbonded steel rods, and these rods were tensioned and they were anchored after hardening of the concrete. So, this is again another very interesting applications by Dill as early as 1925 of how to use unbonded steel rods for pre-stressing applications. Then in 1926, Eugene Freyssinet from France, he is also called as father of pre-stressed concrete, because he has been credited with employing high tensile steel wires as high as 1725 megapascal. Because in the earlier attempts of pre-stressing, they were not very successful because of losses in pre-stress. So, Freyssinet was able to understand that if you use high tensile steel wires, I can go for large amount of tension. Even if some tension is lost due to loss of pre-stress, still significant amount of pre-stress will be still left in concrete. So, it will not adversely affect the performance. So, he is also developed conical wedges for end anchorages, and he also developed double acting jacks. These are all some of the very significant contributions of Eugene Freyssinet. That is why he is also called as father of pre-stress. And then in 1938, Heuer in Germany, he invented a very nice method called long line method of producing precast elements and pre-stressing them. So, that's a technique called pre-tensioning method, which we will discuss what is pre-tensioning, post-tensioning in detail in the coming modules. But Heuer is the one who invented this long line method of pre-tensioning, where it is used to produce pre-tensioned precast elements. Then in 1940, Gustav Magnel from Belgium, he developed anchoring systems for post tensioning using flat wedges, and then the pre-stressing application actually flourished throughout the world. Then Ulrich Finsterwalder from Germany, he is also is one of the pioneer. He has been credited for developing a balanced cantilever construction method of bridges, which is a very popular method of constructions even now in variety of a number of locations. And balanced cantilever method is a commonly used method for bridge construction throughout the world. Now again, Professor Gustav Magnel, as I have explained you, he illustrated the concept of pre-stressing through this nice stacking of books, and he expanded the ideas of Eugene Freyssinet to English speaking world, and he also characterized the potential of pre-stressing, and this is one of the very famous application, Walnut Lane Bridge in Philadelphia, which was one of the first bridge using pre-stressed in the year 1951 with a span of about 48.5 meter main span. So, he actually helped in promoting the applications of prestressing in North America. Again, now let us see what are the variety of applications in India, and you can see that in India the applications of prestressed concrete, in fact it started as early as 1940s. First applications were for airport hangars built by British Indian Army at Meerut and Karachi, that is erstwhile, which was in India before partition, and that was the first applications of using pre-tensioned elements for constructing long span roof elements for building airport hangars. Then for prestressed concrete bridge, first bridge was built in 1948, and in fact that is again using pre-tension precast concrete girders of 60 feet and 40 feet spans, and they were built to connect the Assam rail link project, which is a very famous project which provided connectivity to Assam to the rest of the parts of the India, and they were used for constructing variety of bridges using prestressed technologies across rivers Teesta, Tosha and Sankosh. And another classical example is this Palman Road bridge at Rameshwaram, and this is a very classic example of using prestressed concrete, particularly in a marine environment. And as you all know, in marine environment concrete can undergo corrosion very quickly if not designed properly, and using prestressing helps you to eliminate cracking, as we have discussed in the previous slides, and this was built using prestressed technology, so that under service loads you do not have any cracks at all. So, the chloride induced corrosions is going to be very negligible because of the design aspect. So, you get better durability and longevity in performance. Right. Again, Mr. Engineer Karnail Singh, again one of the pioneers in promoting the prestressed technology in India, and he was actually the chief of this Assam rail link project that we discussed in the previous slide. And this is also another nice applications of Kolio-Bomara bridge in Tezpur in Assam, and you can see this is a prestressed concrete box girder bridge, and it is done using segmental cantilever construction, where the precast segments are progressively prestressed, okay, from one end, either end. So, that is why it is called as balanced segmental cantilever constructions. And you can see there were multiple spans like this, it was built using prestressed concrete box girder using segmental cantilever construction. And in fact, this bridge was designed by Gammon India, and another important pioneer in promoting prestressed concrete application in India is John Gammon, who started this Gammon India Limited, and this one of the pioneering Kolio-Bomara bridge was actually designed by Gammon India, and they were designed to resist heavy flood and seismic activity, which is very common in Assam, right. So, these are some of the pioneers that they have helped in promoting prestressed applications in India. We also have again another important consultants, Stoop Consultants. They are also one of the pioneers in promoting precast and prestressed constructions in India, and this is a very nice example of how we can use prestressed technology. This is a very interesting application, which is a prestressed aqueduct. Basically, it is to transport a canal water from one end to the other end, and you can see the total length of this entire aqueduct is about 947 meter, and each span is about 41.5 meter. Okay, you can see, and it runs for almost a kilometer, and it is in operation from 1985, and this is the first aqueduct in India that was done using match precast segmental construction. So, that means the elements were done so that the end surface are going to match when you put everything together. This also have both longitudinal as well as prestressing in the transverse direction. Okay. So, this is very one of the thing. Again, Mr. Chandar Alim Chandani is one of the pioneer who was very instrumental in promoting the precast and prestressed applications in India. And again, as I've told, Stup Consultants is again one of the very pioneers in promoting prestressing in India. Now, let's talk about why do we need prestressing. Okay. So, this is a good example to illustrate how we can use prestressing and how that can be used for increasing the load before the system is going to crack. Now, I have three cases. The first case you can see here, it is a plain concrete beam. Okay. It is a plain concrete beam and we have a 6 meter length. Okay. And the cross section I will show you in the next slide. Okay. This is a plain concrete beam. Now, if I start increasing this load W1, we want to see at what load it is going to crack, right. Now, the second example is the same beam, same cross section. Now, if I am squeezing this beam by applying a compression like this, okay, and the amount of compression that I have chosen is 750 kilonewton. Now, I want to understand the same beam, same span, in the presence of this compression force of 750 kilonewton, what load at which it is going to crack. This is a case of a concentric prestressing. Concentric prestressing. Okay. So, this is a concentric prestressing. The third one is an eccentric prestressing. We can get more benefits out of it. So, same compression force. Now, I am going to apply at an eccentric distance. So, this is the eccentric distance, okay, the eccentricity of the prestressing force. This E I have taken here as 200 millimeter. Let us understand now these three cases and see what is the effect of this prestressing. One is I just apply the prestress at the CG of the cross section along the length of the beam, and the second case is I am applying this prestressing at a distance of eccentricity 200 mm from the CG of the beam. Okay. Let us see how these load capacities of these beams before it cracks. Now, let us look at the first example, which is a plain concrete beam, and you can see the section that I have chosen is 300 mm and 500 mm. And I am also taking this is 40 megapascal. So, 40 megapascal is the cylinder compressive strength, okay, cylinder compressive strength. Okay. Now, you can ask me what is a cylinder compressive strength. So, typically we use cube for testing concrete material strength in compression, but it is not exactly represent the true material strength of the concrete, you know. So, I have taken here cylinder compressive strength, which is a true representation of the material behavior of the concrete. Now, you know that flexure from basic flexure theory, you know that from Euler bending theory, I can calculate the stress in the concrete by F by Y is equal to E by R. So, this is your basic bending theory, right. Now, I want to calculate at what moment it is going to reach the flexural tensile strength, right. Now, what is this F? F here should be flexural tensile strength, right. So, what is flexural tensile strength? The flexural tensile strength is nothing but modulus of rupture, which is what this FCR is, which is modulus of rupture, right. So, as you can see, the modulus of rupture is a flexural tensile strength, which is typically given by 0.7 square root of FCK. Now, what is FCK? FCK is a characteristic compressive strength of concrete, characteristic compressive strength, and this is a cube compressive strength. Now, there is a relationship between cylinder and cube compressive strength, and so if you the cube strength is typically 1.25 times F prime C, and I have to subtract also 1.65 times the standard deviation, right. because characteristic strength is the strength of the material only. You are expected to have 5% failure. It is a 95%. 95% of the samples are expected to have value above the characteristic strength. You know that. You have studied in reinforced concrete design, right? So the characteristic strength, if you see, I have to get FCK as 1.25 times 40 minus 1.65 times 5. 5 megapascal is the standard deviation for a concrete, right? So you get roughly about 41.75 megapascal. If you calculate, it is going to be FCK. So FCR is going to be, if I put 0.7 into square root of 41.75, I get 4.52 megapascal. This is the flexural tensile strength of the concrete. Now that I know FCR here, I have calculated to be 4.52, I can calculate what is the load at which it is going to fail. Now how do I calculate that, right? So you can see here, this, if I take this critical cross section at the loading point, that's where the maximum bending moment is going to be there. And now for this, you can actually quickly calculate what would be the moment. Moment will be equal to W L by 4. So you know the W, that's what we are trying to calculate, and L is given to you as 6 meter. Now I want to calculate W in such a way that when FCR reaches 4.52 megapascal. So again, I am taking this as tension and this as compression. So I am taking positive as tension, compression is negative, right? So you see here, if you go back and put your basic bending equation, we can write the stress by the distance of the extreme fiber y from the neutral axis should be equal to m by I, or in other words, moment is given by sigma into Z, right, where sigma is your stress. Now we want to calculate what is the cracking moment, right? So what is the cracking moment we want to calculate? What is the cracking moment? Cracking moment is stress multiplied by section modulus, which is Z we know, which is equal to I by Y, right? So we do that. So you can see here, now what is the stress at which it will crack? We have calculated flexural tensile strength is 4.52 megapascal. So I put this 4.52 here. And what is the section modulus? Section modulus for this particular section is Z is going to be B H square by 6. So I substitute B, H is 500 square, and then the units, everything we are multiplying it, right? And I want it in kilonewton meter, that is why I multiplied by 10 to the power of minus 6. So if you substitute that, you will get the moment at which it is going to crack is going to be 56.5 kilonewton meter. Now what would be the corresponding load which will create a moment of 56.5 kilonewton meter at mid span? So we know that M is equal to W L by 4. So from here I can calculate my load that will induce this moment. So that is going to be equal to W crack, which is M crack into 4 by L. So if you substitute the values, how much load you are getting? You are getting a load of 37.67 kilonewton, which is the load at which this plain concrete beam of cylinder strength of 40 megapascal will crack. When the bottommost fiber is going to reach 4.52 megapascal, it is going to crack like this, right? And then, right, maybe the color I will take this. So it is going to crack like this, there is no reinforcement and it will just fail, right? And because there is no reinforcement to intercept the crack. So this is the load at which it is going to crack for a plain concrete beam, right? Okay. Now let's go to the next case. This is the case, okay. Again go back, this load is 37.7 kilonewtons. So please remember this number and let's look at the next case. Now we are going to the case 2. What is the case 2? Same cross section 300 by 500 and the same length 6 meter. Now I am also applying this concentric prestress of 750 kilonewton, right. So, basically I am squeezing the concrete and putting it in some compression. Now, let us calculate what is that compression, right. And again my idea is to calculate what load at which this is going to crack, right. Okay, let us calculate. Now, what is the level of pre-compression that we are putting? So, I am applying this pre-compression at the cross section. So, compressive stress is going to be P by A, which is 750 into 10 to the power of 3 divided by what is the cross section? It is 300, 500, which will work out to be, if you see that, it is going to be 5 megapascal. So, that is what we have written here, P by A, which is 5 megapascal, right. Now, you see here, what previously we have calculated my FCR, flexural tensile strength is 4.52 megapascal. So, this is from pre-stress and this is from load, external load. This plus this should give me this kind of a profile where the bottom fiber should reach FCR, right. So, that is the idea. So, I have applied a 5 megapascal pre-compression and this, so that this 5 has to, so when this 5 minus 5 will become plus 4.52, due to external loads I should be able to apply 9.52 of tension. So, I need to apply 9.52 megapascal of tensile stress from the external load, then only this pre-stress plus this externally load induced stress will give me a bottom stress of plus 4.52 or tensile stress of 4.52 megapascal. So, now we can calculate from this plus this is what should produce this. So, how much load it is required to create this 9.52 megapascal stress on the tension most fiber. So, now let us look at that. So, you see here again the basic thing is this, sigma crack times Z will give me M crack. Now, what is sigma crack that I need to put? Now, what is that value that I need to take? I need to take this value, right. So, basically if you see here 9.52 is the stress that I need to apply externally, so that the net stress will become tension of 4.52, right. So, previously if you go back, how much we calculated for? We calculated only for 4.52. Now, how much stress I need to create due to external load? Now, I need to create 4.52 plus 5 megapascal, then only I will be having a net tension of 4.52. So, now higher the stress, higher should be your moment at cracking. So, that is what we get, which is 119 kilonewton meter. Now, if you substitute and calculate what is the load required to crack, then you can see here it has become 79.33, which is more than double that of what we had for plain concrete. Okay. So, that is what we have. So, you can see here just by applying this 5 megapascal compression, the load at cracking has increased significantly. And now, I want to even make it more efficient. The same compression, now instead of applying in a concentric way, if I am applying it in an eccentric way, then I get more benefits. So, let us look at that in the next case. So, that is what we have, concrete beam with eccentric prestressing, same, everything same. Now, only thing is, now this is my eccentricity from here to here, that is your eccentricity, which is 200 millimeter, right. And so, if you see again now, this is axial component still remains same, which is 5 megapascal. Now, in addition to that, now if I am applying also prestressing moment, how much I am applying, which is P into E, that means 750 kilonewton into eccentricity, which is 0.2. So, this is a moment that I am applying, right. So, this is a moment that I am applying. So, I am applying almost 150 kilonewton meter due to prestress. Now, where is that eccentricity? Eccentricity is at the bottom. So, the bottom fiber will be in compression, top fiber will be in tension, right. Now, what will be the stress that will be introduced due to prestress? This is due to prestress. This is due to axial stress, again from prestress. This is moment due to prestress moment, okay, MP. Okay. So, if you see here the stress, how do we calculate? Again, moment is divided by section modulus. P into E is we calculated 150. Section modulus we have already calculated, which is BH square by 6. So, 300 into 500 square by 6. So, if you substitute that, you will get a negative 12 megapascal. That means this is in compression. This is also negative in compression. Now, here this is going to be, is what we are calculating. Now, what is that? This plus this should come up with this. Now, again, what is this? This is due to load. Okay. So, the load will create tension at the bottom, compression at the top, right. So, now how much I should ascend so that the net will become plus 4.52. So, you should see minus 5, minus 12, then plus some x should give me 4.52. Now, what should be the x? X, you can see that it is going to be equal to 21.52 megapascal, right. So, I should create a stress of 21.2 megapascal, 21.52 megapascal from external load, then only this bottommost fiber is going to be in tension, it will lead to crack. Now, you see here, now I am applying a very high stress, okay, due to external load. So, now let us calculate now what is that we are getting to get out of it. So, you see here again stress moment at cracking is going to be stress at cracking multiplied by section modulus. So, stress at cracking now it is going to be 21.52. See, the first case we had only 4.52, then we increased it. Now, because of eccentric prestress, now again I am going for a very high magnitude. Okay. So, this is a one big advantage, sigma crack into Z. So, if you substitute that, I am getting a cracking moment of 269 kilonewton meter, and then if I put it in the load equation where moment equal to WL by 4, and if I calculate my W cracking, then I get my W cracking as 179.33. So, you see it is a very high increase in your load at cracking. Now, one catch here, I just wanted to explain this here. Now, you see what is the problem with this is, now if external loads are not there, what would be the stress at the top? Let us say that I do not have the, okay, let us say that I do not have this. So, if I have only these two, no load, then what will be the net stress at the top? It will be minus 5 plus 12. So, what is that you will get? You will get plus 7 megapascal. Is it good or bad? So, in this case, purposefully we have chosen numbers in such a way to illustrate that sometimes if you apply too much pre-stress, you will have problem. Why is it a problem? If no external loads are acting, only due to pre-stress, now top is getting into plus 7 megapascal, which is greater than your FCR. That means, if you put too much pre-stress, you can also have cracking at the locations where you do not want. Okay. So, that means the top fiber can get into tension and it can lead to crack. So, purposefully we have chosen slightly a higher number to illustrate this point, but typically we do not do that. Okay. We have stress limits are kept so that you do not apply too much pre-stress also, right. So, now let us summarize this example. The first case we had 37.67 kilonewton. The second case I am able to apply almost 79.33. So, that means increase, right, 131 increase, that is a load that we can get. In fact, it should be double, right. I think this number is wrong. Okay. So, this is not correct. So, you can get 79.33 divided by 37.67. So, that is the amount of increase that we are getting. And the third case you can see here almost it is increased 179 by 37.6. So it's again you are getting high increase in capacity for right. So that much times increase in your cracking moment loading capacity. So 179.33 divided by 37.63 is the increase in capacity. So you can see here, by applying pre-compression, I am able to get very high increase in your loading at cracking. Okay, that's the idea. Okay.